Hello everyone. Let's analyze. So today we're going to continue our discussion on integration. By now you should have seen the video on Riemann integrability with the animations of the upper sums and lower sums and the definition of what it means for a function to be integrable, at least according to Riemann. So today we're going to prove two theorems focused on for what classes of functions are we guaranteed integrability. So our goal for today is to prove that if f is continuous on a closed interval, then it's Riemann integrable. And if f is an increasing or decreasing function on a closed interval, then it is Riemann integrable. Right? So these are today's goals. So before we get started in rigorously proving these theorems, a bit of notation to help us along the way. Just as a reminder of the upper and lower sum. And again, you should have seen this illustrated in the previous video. And if you haven't watched that video, I would recommend that you stop here and watch that. So the upper sum is the sum of rectangular areas, where the height is the supremum of f on a subinterval in a partition P times width, right, which is the width of the subinterval of that partition. The lower sum is again a sum of rectangular areas where the height is the infimum on the subinterval times the width of the subinterval. Just to simplify some of our notation and save some ink, we'll say that the supremum over a subinterval will be denoted by big M, J, or J, the jth subinterval, and little mj will be the infimum of f on the subinterval. Right? Sometimes I'll drop the of f if it's clear what function we're talking about. For example, we see here that we can write the upper and lower sum much more simply. Here we have height times width. Height is the supremum. Here we have height times width. Here the height is the infimum of the jth subinterval. Right? You see that I've dropped of f because it's clear that we're talking about a function f. Right, so now the upper sum and the lower sum can be written just a bit more simply. We can see that it really is a height times a width. And just as a reminder to some of the notation that was introduced in the video, the upper integral is the infimum of all upper sums. Right, we know that the upper sum is greater than or equal to the integral if it exists. So if I take the smallest possible upper sum, or the infimum of this set for every possible partition, I get what's called the upper integral. Some shorthand for how I might write that as the infimum over all partitions P, U of Fp. Right? So this might just be a shorthand for this. Similarly, the lower integral is the supremum of all lower sums for every possible partition. Right? Again, if the integral exists, the lower sum is less than or equal to it. So if I take the biggest possible one, right, I call that the lower integral, and I will typically write it this way. And if these two values agree, that is if they're equal, if the lower integral and the upper integral are equal, then we say that f is Riemann integrable on the interval a to b. And specifically the integral is equal to these two values. Okay, so let's get started. So to help us along the way, we're going to prove a few lemmas. The first lemma we're going to prove is that if P prime is a refinement of the partition P of the closed interval a to b, then the lower sum of the original partition, the unrefined one, is less than or equal to the lower sum of the refined partition P prime. And the upper sum over the refined partition is less than or equal to the upper sum of the original partition. And this is something that was hinted at in the animations that you saw on Riemann integrability. Now, what do I mean by a refinement? Well, what I mean is that if P prime is a refinement of P, then P is a subset of P prime. Or remember that both P and P prime, if they're partitions, they're just a finite set of points that are strictly increasing, going from A to B. So for example, one partition could be A is x0, x1, x2, x3, and B is x4. That's a partition. Right? So that could be, for example, P. And to refine the partition is just to add extra points. So if I add extra points there in red, if I were to take the original points plus the red points and call that P prime, that would be a refinement. So in order to prove our result, let's add the points one by one. So let's let P0 be our original partition. And let's let P1 be the original partition with just one more point. So P and then A1, where A1 is in the refinement, but not the original partition. We'll let P2 be P1 plus just one more point, where A2 is in the final refinement, but not in P1. And we continue adding points one by one so that PK is PK minus 1 and a new point AK, where AK is in the refinement but not in the previous partition. Well, if we add points one by one, eventually we'll get to the refinement. In other words, there is an L for which PL is the refinement. So let's compare the lower sum on sum PK and the lower sum for PK plus 1, where there's only a difference of 1 point in the two refinements. So we'll let AK be that point that's added. So AK is in PK, but not PK minus 1. And we'll say PK minus 1 is, well, it's a partition. And I'm adding to this partition AK. AK is going to fall in one of the closed sum intervals. So let's say AK is in XK, XK plus 1. In fact, these actually should be open intervals because it's not one of the previous partition values. So the lower sum of F over PK is right, the infimum over the subinterval of F times the width of the subinterval. Remember our shorthand for this. Right, so that's M1 times delta X1 plus M2 times delta X2 plus the kth one right, all the way to, well, the n minus 1, 1. Now, let's look at this kth term. This kth term is equal to mk times xk plus 1 minus xk which is equal to mk times xk plus 1 minus ak plus ak. I'm essentially adding 0 here. Which is mk times xk plus 1 minus ak plus mk times ak minus xk. Right, and again, that's just for this one term here. This is this one term here. Can be broken down in this way. All right, now let's consider the lower sum for the partition pk plus 1. So pk plus 1 is x0, x1, x2, xk, ak, xk plus 1, xn. Right, because I essentially just took this partition and added an extra point. So the lower sum for this one extra term refinement is m1 times delta x1 plus m2 times delta x2 plus, now when we get to this subinterval, it's the infimum over xk to ak of f times ak minus xk plus the infimum over ak to xk plus 1 of f times xk plus 1 minus ak plus, and after that the intervals are the same as before, so we just get the same terms in our summation. Now here's the key idea. If I take the infimum over xk to ak of f, it's greater than or equal to the infimum of over xk to xk plus 1 of f of x, which is, by the way, mk, right? Because this interval, right, is equal to the union of xk to ak and ak to xk plus 1. Similarly, the infimum over ak to xk plus 1 of f is also greater than or equal to mk. Right? So if I were to take the difference right, then every term except for those surrounding the kth entries are the same. So what I would get is the infimum of f over xk to ak of f times ak minus xk plus the infimum over ak to xk plus 1 of f times xk plus 1 minus ak plus mk times ak minus xk plus mk times xk plus 1 minus ak. Right? Every other term agrees and is therefore 0 once I subtract. Because this is greater than this, and this is greater than this term, this is greater than or equal to 0, which implies that if I refine by 1, I get a greater than or equal to lower sum. But remember here that k is arbitrary. K could have been that first single refinement or the last one. That means that L of f over the refinement, right, that's L of f PL, is greater than the lower sum of the previous refinement, which is greater than the lower sum of the first refinement and all the ones in between, which is greater than or equal to the lower sum of P naught, which is the original refinement, right, which equals the lower sum of f of P. And we've proven our result. Of course, you might ask, well, wait a second, what about the upper sum result? Well, the upper sum is proven similarly, and I'm completely confident that you would be able to do that on your own. In fact, it would be a very good exercise. So the next lemma we're going to need will prove that the lower sum is always less than or equal to the upper sum, no matter what partition you're looking at, even if the lower sum and the upper sum are computed over different partitions. So for any partition P and Q of the closed interval a to b, the lower sum over the partition P is less than or equal to the upper sum of the partition Q. And again, P and Q are arbitrary. Well, we know that the lower sum over P is less than the lower sum over the partition P union Q. Well, how do I know that that's true? Well, what do I mean by P union Q? Well, remember, P and Q are just a finite set of points. If I put them together, what I have is a refinement of P. And we proved that in the previous lemma, this inequality. Now, that's less than or equal to the upper sum over the same partition. Now, how do I know that's true, that the lower sum is less than or equal to the upper sum over the same partition? Well, again, if we remember the pictures of what these look like, I think this inequality should be clear. But these are sums of rectangular areas, and because I have the same partition, the width of each rectangle is the same, but the height here is the supremum of f, right, the smallest upper bound, and the height here is the infimum of f, the greatest lower bound. Of course, the greatest lower bound of the same set is less than or equal to the smallest upper bound. And because, again, P union Q is a refinement of Q from the previous result, I get that. And we've proven it. Hey, that was pretty quick. So one more lemma before the main event. In the previous lemma, we proved that the lower sum is always less than the upper sum, no matter what partitions we're looking at. So here we're going to prove that the lower integral is always less than or equal to the upper integral. Of course, if they're equal, then we have integrability. So we know that the lower sum for any partition P is less than or equal to the upper sum for any partition Q. So if I were to take the set of all lower sums, right, for partition P of A to B, right, so the set of every lower sum, and if I were to take the set of every upper sum for partitions Q of A to B, then every element of this set is less than or equal to every element of this set, right? This is just a restatement of our previous lemma. Well, if every element of this set is less than or equal to every element of this set, then the supremum of this set, which I'll use my shorthand, is less than or equal to the infimum over every partition of this. And remember, this is the definition of the upper integral from A to B of f, and this is the definition of the lower integral. Of f of x from A to B. And that proves our result. And now we have the main event, where we prove that if f is continuous on a closed interval, then it's Riemann integrable on that closed interval. So let's prove the result. And here's our goal. What we want to do is we want to show for any epsilon, there exists a partition P of the interval A to B for which the upper sum minus the lower sum is less than epsilon. Of course, we also know that this is greater than or equal to 0. If that's true, right, so if true, our goal statement, then if I were to make the upper sum as small as possible, and make the lower sum as big as possible, then this is 0. Because if it wasn't, well, I could find if it was a positive number, that would be contradicted by the fact that I can find a partition so that this difference is less than, let's say, half that positive number. Now, since f is continuous on a compact domain, right? This is compact. Then f is uniformly continuous. That was one of the main results from real analysis 1 when we talked about compactness. What does it mean that f is uniformly compactness? Well, let epsilon be an arbitrary positive number. There exists a positive number delta such that if x and y are in my interval a to b, and the difference between the two is less than delta, then the difference between f of x and f of y is less than, well, really any positive function of epsilon that I want. And I want this, right? The fact that f is continuous, meaning it's uniformly continuous, meaning a delta exists, guaranteeing this inequality. Now, suppose that P is a partition of A to B, and every subinterval has a length less than delta. Right, so every single one for j equals 0 through n minus 1. Right, so on every subinterval, for any two values in the subinterval, this is true, meaning this is true. Well, the difference between the upper and lower sum is the supremum over the interval minus the infimum over the interval times the interval length. Now, remember that this is the supremum of f in the subinterval. This is the infimum of f in the subinterval. This subinterval is itself a compact set, which means I can actually think of this as a maximum and a minimum. However, the max and the min inside of an interval for which this is guaranteed can be no bigger than this. Because if I evaluate f of x and f of y for any two values, it has to be strictly less than this value here. That means this is less than or equal to epsilon divided by b minus a times xj plus 1 minus xj. Now notice this term here is not indexed by j, so it can actually be factored out. And what I'm left with is a telescoping sum. What do I mean by that? Well, if I factor out this term, I'm left with x0 plus 1 minus x0 plus x2 minus x1 plus x3 minus x2, so forth and so on, plus x n minus 1 minus xn minus 2 plus xn minus xn minus 1. You can see that this x1 and this x1 cancel. Will cancel in red, so it looks extra bloody. x2 minus x2. There's a negative x3 hidden deep down in the dot 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 here. There's also a positive xn minus 2 hidden in these dot dot dots. This xn minus 1 and this negative xn minus 1 cancel. And I'm left with epsilon over b minus a times xn minus x naught. Well, remember, xn is b and x naught is a. And that's just epsilon. Which means we have proven our goal. We've satisfied our goal. Because epsilon was arbitrary, our goal result is true. For any epsilon, there is a partition for which the difference between upper sum and lower sum for that same partition is less than epsilon. Meaning that the infimum of the upper sums, remember this is the upper integral, minus the lower integral is 0, meaning the upper integral and the lower integral are equal. And that gives our result. And now we come to the second class of functions for which we are guaranteed Riemann integrability, increasing or decreasing functions. Well, suppose that we consider the case of an increasing function. Suppose that f is increasing. Now, let P be an evenly spaced partition. With subinterval lengths b minus a over n. In fact, let's add a subscript to p to denote that it's a evenly spaced partition with n subintervals. By the way, each entry of Pn would be a plus j times b minus a over n, as j goes from 0 to n, in case you were wondering. By the way, that might be useful in your homework. Then the difference between the upper sum and the lower sum for this particular partition is the supremum minus the infimum times my subinterval length, which for each and every one is b minus a over n. Now remember that big M is the supremum of f over a subinterval. But since f is increasing, this is equal to f of xk plus 1. Right? It's equal to f at the right side of the subinterval. And this is the infimum. But again, since f is increasing, this is f evaluated at the left side. We know that f of xk is less than every value of f on that subinterval, or less than or equal to. And since it's a member of the set, it's the infimum. So then what we have here is another telescoping sum. So this equals f of xn, which is f of b, minus f of x naught, which is f of a, times b minus a over n. Now notice that f of b and f of a are, well, they're fixed numbers. So is b and a. But n is arbitrary. N can be as large as I want. In fact, if I take the limit as n goes to infinity of this difference, I get 0 because I have a fixed number divided by n, and n can get arbitrarily large. Now, this is equal to the limit as n approaches infinity of the upper sum minus the limit as n goes to infinity of the lower sum. So consider this sequence. Every entry of this sequence is an upper sum for some partition. It is, every entry of the sequence is greater than the infimum over every possible partition. Furthermore, if I subtract the limit as n goes to infinity of the lower sums, right, each of these lower sums is less than the supremum of the lower sum for all partitions. So if I have the negative, then it's greater than the negative supremum. Which, by the way, remember that this is greater than or equal to 0. That was the third lemma we proved. Right? This is the upper integral, and this is the lower integral. The upper integral is greater than the lower integral, so their difference is non-negative. So it's bounded below by 0, and it's bounded above by 0. Well, if it's bounded below by 0, and it's bounded above by 0, then it's 0. That means this is equal to this, and this is the upper integral. Which is the definition of Riemann integrability. So we've proven our result. That's it for now.